MacMaths, let's do some maths today. Statistics. Okay, so we're looking at tree diagrams. Actually, this is the fourth lesson I've done today on a bank holiday, so I'm actually losing the will to live. Okay, but I'm going to go through the tree diagrams for you. There's actually, so this is exercise 5D in the AS book. There's actually nothing that is any different from GCSE. But if you've not done them since GCSE, then I'll just remind you. Okay, so let's have a look at what tree diagrams are, or how they work. Okay, let's get a blue pen. So let's just have a look at the classic, the classic question. 3 milk chocolates and 2 dark chocolates. Okay, so this is what's going to happen. You're going to choose 2 chocolates at random from the bag, and in this bag there's 3 milk and 2 dark. Okay, so tree diagrams is just a way of giving you a timeline to what could happen. Okay, so what we're going to do, there's 2 situations here that you always get. There is replacement and non-replacement, so we'll look at both. I'll remind you of both. First of all, okay, we'll do replacement. So that means you take a chocolate, you look at it, and you resist the temptation to stick it in your gob, and you put it back in the bag. Okay, so let's have a look at that. So, so they're the simpler ones to do because there's less maths to do. So your first choice, you can either have a milk or a dark chocolate. So you write the letter or the abbreviation on the end of the line from a starting point. And the probability of choosing a milk, well, there's 5 altogether and 3 of them are milk, so you've got a 3 out of 5 chance, which means you've got a 2 out of 5 chance that choose dark, and you'll notice they add up to 5 over 5, which is 1. All probabilities add up to 1. Now, only one of these things, it's a timeline, and only one of these things in real life would actually happen. So say this happened, and you chose again, and you chose a milk. Well, remember, we put it back in the bag. So to get another milk, it's 3/5. But the second time, if you get a dark, it's 2/5. Okay. Now, none of that happened because what actually happened the first time, you chose a dark. So you put it back in the bag and you chose again, and you could have got a milk, which we know is 3/5, or we could have got a dark, which we know is 2/5. Okay. So this is your tree diagram for 2 choices. Okay, so doing it once, doing it twice, and only one of these happens. So each one is a possible timeline, and I like to write those out as in milk, 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 dark, dark milk, or dark, dark. So remember that only one of these situations actually happened. You know, if you did that experiment, you'd either get 2 milk, a milk followed by a dark followed by a milk, and a dark followed by a dark. And then the probabilities, because they're independent, choosing this one is not dependent on that one. So choosing this one, no matter what happens before, you remember we times them out. So you times down. So 3 times 3 is 9. 5 times 5 is 25. Because this one is in fractions, it lends itself to fractions. So keep them in fractions. 3 2s are 6, 6 over 25, 2 3s are 6 over 25, and 2 2s are 4 over 25. If you add all of those up, of course, you get 25 over 25, which is one whole one, which you should do. If it now said the question was, what's the probability of getting 2 milk? You can see it's 9 over 25. If they say what's the probability of getting 2 dark chocolates, it's a 4 out of 25 chance. If the question says what's the probability of getting 2 chocolates that are the same, then it's this or this. And remember, we add those 2 together, so that would be 13 out of 25, wouldn't it? What would be the probability of the 2 chocolates being different? Well, it could either be this one or this one, so that's 12 over 25. So we can add those up at the end, you know, combinations of those if we want. Okay, and that's just your standard tree diagram. Now, let's just say let's just rub those out, and let's rub these out. I do it with sort of cups and actually labelled cups sort of when I do this in class with my year 10s. Okay, so let's just say we have a situation where we don't replace. Okay, so in other words, we eat the chocolate. So let's just say this happened. If we had a milk chocolate and we chose milk, okay, and we ate it, okay, then milk, 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 dark, dark. So I've drawn, this is what we start with, 3 milk and 2 dark. And if we choose and get a milk and eat that milk, we're left with 2 milk and 2 dark. So the probability of getting a milk is now 2 out of 4, isn't it? And the probability of getting a dark is 2 out of 4. Okay? If that didn't happen, and if this happened and we got a dark chocolate and we ate it, okay, the probability of getting a milk now, well, there's still 3 milk left out of the 4, but there's only 4 left. And the probability of getting a dark, well, there's only 1 dark now because we've eaten 1, and there's only 4 left. Okay, so you can see that changes now, and that's a non-replacement situation. So 3 2s are 6, so that's 6 out of 5 4s are 20, and that's 6 out of 20, that's 6 out of 20, and actually that's just 2 out of 20. And if you add those all up, they come to 20 out of 20. Okay, and again, what's the probability of getting the same flavoured chocolate, eating the same flavoured chocolate? Well, it's that and that, so it'd be 8 out of 20, and then you can cancel down at the end, and so on. Okay, so there we go. Sometimes the second one is dependent on the first one happening, okay, and I won't explain that now. You'll see that in a question. Okay, so we'll do some of the questions. Okay, so that's it. You can have a go at those. This is exercise 5D. Have a go at those questions. Okay, before you then watch me do the next bit, because what I'm going to do for the next bit is, because this is unbelievably dull and I've been doing it all day, I'm going to miss out questions 1, 2 and 3, which are the first 3, probably the easier ones, mixtures of fractions and decimals with tree diagrams, and I'm going to do 4, 5 and 6, which they are saying are they're all 4, 5 and 6 they're saying are exam questions, so I'm going to do those 3 exam questions with you. Okay, and here they are. So have a go at those first ones first, have a go at 4, 5 and 6, and then okay, you can watch this part of the video of me sort of going through them to check your answers and check your thinking, but you may check the back and find out you did them all okay and so on. So all good, you don't need to watch this next bit then. So here we go. Question 4. So this is where there's an influence. Okay, so what happens, the second part is dependent on the first part, and this is Mr. Dixon who plays golf. Okay, so here he is, Mr. Dixon who plays golf, and he tees off and he plays the first hole. Now if he does well and he gets par or under, okay, so that's what all golfers are trying to do, aren't they? Get par or less than par. In other words, get it down the hole in the smallest number of things. So I'm going to do that. So less or equal to par. That's what it says. Less or equal to par on the first hole. The probability of that happening is 0.7. Now that means that the probability of him getting greater than par must be 0.3, because they've got to add up to 1. This one's in decimals, isn't it? Okay. Now he goes on to play the second hole, and on the second hole he gets and it says this is dependent. So if he's done well on the first hole, his confidence is up, he's having a good day, he's playing well. Okay, so the probability he gets less or equal to par on the second hole is now actually 0.8. Okay, he's well up for it. He scored par, so he's happy with that, or he scored less than par, he's really happy, so he's 0.8. So that means on the second hole, if he's done well on the first one, there's only a 0.2 chance that he goes over par on the second one. Okay. However, it does say that if he doesn't do well on the first hole, okay, the probability that he gets less than par and pulls it back is 0.4 on the second hole. So he's done badly on the first hole. Now he's got much less of a chance of doing well on the second. In fact, only 0.4, less than half of the time he only goes on, because he's a bit miserable then. He's upset, you know, he's not playing well, and it's got to his head, and he's one of those that's affected by how he's playing. Or it might be a bad day, he's having a bad day. So therefore, greater than par, there's a good chance, more than half, that, because they've got to add up to 1, that he does bad on the second one as well. So there we go. Okay, now this is a tricky one, this one, because it's not tricky really. It's just like, I like to label them, but you know, you got these, I like to like M and D. You can't put like your milk and your dark here, can you? And so on. So anyway, but let's have a look at it. It says draw a tree, so we've done that one. Yeah, got our mark for that. Is it independent? No, it's not independent, because the second one depends on how well he does on the first one. That's obvious, so just a statement. And it says, what's the probability that he gets par or under on only one hole? So par or under on only one hole, that's, he gets par or under on this one, but not on that one, so it's this route, isn't it? So it's this route, so par or less than par and over par, or he goes over par, so not on that hole, but then on this one he does do it, so that's only one hole. So it's these two, a combination of these two. And 0.7 times 0.2 is 0.14, 0.3 times 0.4 is 0.12, so the answer to that is those two added together, which is 0.26. Okay, and that's your first one, number 4 done. The probability that he gets par or under on just one of the holes is a combination of those two outcomes, which is 0.26 added together. Okay. The next one is one of those ones that I dread. The next two are actually, just because they're just time consuming. A bias coin is tossed 3 times. Okay, nightmare, because you've got to go heads, tails, and it does say draw a tree diagram. Damn. Okay, so you've got to go heads or tails with the second, heads or tails with the second. Now you do it a third time, and if you've got 2 heads, you could go heads or tails, heads or tails, heads or tails, heads or tails. So a nightmare, you've got to do all of that, and it tells you that the probability that you get heads is 1/3 each time, so that means it's 2/3 chance you're more likely to get tails. So you've got to fill in now 2/3. You've got to put 1/3 on every heads and 2/3 on every tails. 2/3, 1/3, 2/3, 1/3, 2/3. Really concentrating here. 1/3 and 2/3. Okay, and I like to finish off. So this is heads, 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 tails, heads, tails, heads, heads, tails, heads, heads, tails, tails, heads, tails, 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 heads, heads, tails, heads, heads, tails, heads, tails, tails, heads, tails, 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 heads, tails, tails, heads, and tails, 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 tails. So those are all the possible outcomes. Right, what's the probability of heads, heads, heads? Times them all out. 1/3 times 1/3 times 1/3. 1 times 1 times 1 is 1. 3 times 3 times 3, 27. That one's 27. Heads only once. Okay, so what's the probability of getting heads only once? So we're looking down our list now. That's that one. That's only got 1 heads in it. That's only got 1 heads in it. So those 3 added together. So that is a heads, tails, tails is a 1 times 2 times 2. 1 times 2 is 2, times 2 is 4, and 3 times 3 times 3 is over 27. Now because they're all made up of 2 tails and a head, when you multiply those out they'll all be 4 over 27, because it's the same numbers just in a different order. So it's a combination of those 3. Okay, so this was 1 over 27, and this one, heads only once, is that add that add that. 4 add 4 add 4 is 12. 12 over 27 is the answer to that. Now this is an interesting one. It says, you do all of this, the whole experiment was repeated again from the start. Find the probability of getting 3 heads or 3 tails on both trials. Okay, well the probability of getting 3 heads or 3 tails, well 3 heads is that, and 3 tails, 2 times 2 times 2 is 8 over 27. So the probability of getting on the first trial 3 heads or 3 tails is 8 out of 27 plus 1 out of 27 is 9 out of 27, isn't it? Which is, cancels down to a third. So the probability of getting either heads or tails on the first is a third. Okay? And the probability of getting heads or tails on the second trial, the second time you do it, then will also be a third, because it's independent of this one, isn't it? It's, you know, you do it again and you've got the same, because it's decided that that's the probability for getting heads or tails. So because they are the two trials are independent of each other, it happening in this one followed by it happening in that one is the third times a third, which of course is a ninth. So the chances of you running this experiment and getting either 3 heads or 3 tails, and then doing it again and getting another, either on the second time you do it, either 3 heads or 3 tails, so it's a third times a third, because they're independent of each other, which is 1/9. Okay, and a lot of work for that, isn't there? And this one, I just don't believe that this was it's saying it's an exam question, and I don't quite believe that, and I'll show you why, because I'm not even going to do the last bit, and you can if you want, but I'm not doing it. 13 tokens, 4 blue, 3 red and 6 yellow, 2 drawn without replacement. So here we go. So it doesn't sound bad at the start. So blue, red or yellow. So you can go blue, red or yellow. And in fact, knowing what's coming here, I'm going to spread it out. Okay, and it's done twice. So blue, red, yellow, blue, red, yellow, blue, red, yellow. Okay, I'm not going to do it all here, and it says, so 13 tokens, because 6 add 4 add 3 is 13. Okay, so that means you've got a 4 out of 13, a 6 out. You've got a, let's do it in a different colour, so 4 blue, 4 out of 13, 6 out of 13, and what was the yellow? Oh no, red, blue. That's 3 out of 13, and yellow was 6 out of 13. Okay, so that's the probability. Now it's done twice, and it's done without replacement. Okay, if it's done without replacement, now look at the first question. It's saying what's the probability of yellow, yellow. So you get a yellow, you do it first time, but you do get a yellow, and you don't put that yellow back in. So that means the second time there's only 5 yellows left out of now only 12 counters, because you took one out and it was yellow. So the probability of getting yellow, yellow is going to be 6 5s are 30, 13 times 12. What is 13 times 12? Is equal to 156. And they will cancel that down in the back of the book. 30 over 156 is the answer, is 5 over 26. Okay, so that's your yellow, yellow happening. And then it sort of says, there's only one mark for it, it says the probability of the third yellow, if it was done another time, what would be the probability of getting a yellow the third time, okay, if the first 2 were yellow. Now it doesn't mean all together, it just means what's the probability of the next one being yellow, independent of those, although they've both been yellow. So all it's saying is, for this next one is, well, the probability of the next one being yellow on its own would have been, there's only 4 yellow left now out of 11, so it's just 4 out of 11. It's not asking you to times that. It's not saying what's the probability of getting 3 yellows in a run. It's just saying, right, you've got to this point now, what's the probability of the next one being yellow? Well, there's only 4 yellows left out of 11 counters, so it's 4 out of 11, that's all. Now, part C, I can't believe this one because it's saying what's the probability of getting all 3 different colours. Now, to do that, you've got to then go blue, red, yellow. So you've got to go, you've got to work out blue, red, you've got to work out blue, red, yellow and write all the probabilities. Remember, taking one off each time. Blue, yellow, red. You've got to then work out red, blue, and then moving on to yellow down here. Red, yellow, blue. And then you've got to go yellow, blue, red, and yellow, red, blue. So you've got to work out all 6 of those, okay? And I mean, in fact, no, it's not that bad actually. You've only got to work out one of them, don't you? Because they'll all be the same. They'll all be the same. Oh, it's not that bad actually. I'll take that back. Let's just work out one of them. And then although the top numbers and bottom numbers are jumbled up, they'll give you the same. Oh, it's not that bad. So, right. So, blue, then getting a red would be 3 out of 12. And getting a yellow would be 6 out of 11. So 4 times 3 times 6, what's that? 4 times 3 times 6 is equal to 72. So it's 72 out of 13 times 12 times 11 is 1716. Yeah, okay, so it's not that bad actually. So that is for one of those, so but all the 6 of those will be the same, so 6 lots of that. So if we go 72 times 6, so 6 lots of that is 432 over, whoops, so hang on, let's do that again. So I'm going to go, so 6 was 432 over 1716 is 36 over 143. So can you see what I did? Once I'd worked that out, I know that times in those 3, although the numbers are in a different order, effectively each time it will be the same top 3 numbers in a different order and the same bottom 3 numbers. So you'll have 72 over 1716 for each one of these. Okay, so it's 72 over 1716 times 6, or 6 over 1, and that gives you, cancelled down, 36 over 143. So that's the probability of getting 3 different colours. You don't have to keep working them out. Okay. Alright, so that's that chapter finished then. So probability tree diagrams is just, there's nothing there that's that isn't the same as what you've covered at GCSE. Alright, so you should be okay with that. Alright, so fill in the gaps, have a go at the questions, get some practice, do the mixed exercise. You might have to go back to those independent, because I always got hung up with the words, those 2 conditions, add them together to be either or times them together if both things happen.